A filament 10 Earth diameters long just tore off the surface of the Sunday. That is not a metaphor. That is a real structure of plasma and magnetic field, roughly 100,000 miles of solar material, lifting away from the photosphere in a single connected arc. The stakes are immediate, and they are planetary. When filaments like this destabilize, they can collapse into a coronal mass ejection, aimed, potentially, straight at Earth. In the next few minutes, we're going to break down exactly what a solar filament is, why this one detached, what happened the last time something this size let go, and the 3 things you need to be watching over the coming days. Stay with us. Let's start with the question everyone asks first. What actually is a filament? It's cooler, denser plasma suspended above the sun's surface by magnetic field lines that arc up out of the photosphere like invisible scaffolding. Seen from Earth against the bright solar disk, these structures appear as dark, thread-like features. That's where the name comes from. Seen from the edge, against the blackness of space, that same structure is called a prominence. Same object, different angle, different name. Here is the single most important thing to understand. Filaments are not stable. They are held up by a magnetic balancing act, tension pulling down, pressure pushing up. And that balance can hold for weeks, or it can fail in hours. This particular filament stretched across a length equivalent to roughly 10 Earths lined up edge to edge. To put that in human terms, you could fit every ocean, every continent, every mountain range on this planet along that thread 10 times over, and it would still have room to spare. Not a local event, not a regional flare. A structure large enough to be measured against the diameter of our entire world, repeated 10 times. Now, bring that back to what actually happened. Solar filaments like this one exist in a kind of suspended animation, magnetic fields overhead essentially caging the material in place. When that cage becomes unstable, through a process called magnetic reconnection, the field lines snap, realign, and release the tension holding the plasma aloft. The filament can do one of several things. It can drift back down and fade. It can partially collapse. Or it can erupt outward entirely, launching billions of tons of magnetized plasma into space. At speeds that can exceed 1 million miles per hour, that eruption is a coronal mass ejection, and it is the real hazard buried inside this story. Consider the mechanism a little more closely, because this is where the exaggeration and the real explanation split apart. The exaggerated read says the sun is destabilizing, that this is some sign of an impending solar catastrophe. That's not accurate, and it's worth saying plainly. Filament eruptions happen constantly. They are part of the sun's normal magnetic cycle, especially now, as we sit near solar maximum, the peak of the roughly 11-year solar cycle when the sun's magnetic field is at its most tangled and active. The real explanation is narrower and more specific. It's not that the sun is doing something unprecedented. It's about where the material goes if it erupts, and whether Earth happens to be standing in the way. That is why timing and geometry matter more than raw size. A filament this long detaching is dramatic to look at. But the actual risk to Earth depends entirely on the direction of ejection, and whether our planet's orbital position puts us in the line of fire. That's the piece the sensational headlines tend to skip. And that brings us to the historical precedent, because we have seen structures like this before, and we know what can happen when the geometry lines up badly. Go back to 1859. A British astronomer named Richard Carrington observed an intense solar flare, and within about 17 hours, Earth was slammed by the associated coronal mass ejection. The result was the largest geomagnetic storm in recorded history, now known as the Carrington event. Telegraph systems across Europe and North America failed. Some operators reported their equipment sparking and catching fire from induced electrical currents, even after they disconnected the batteries. Auroras, normally confined to polar latitudes, were visible as far south as the Caribbean. That event happened in a world without power grids, without satellites, without the internet. Today, the same magnitude of storm would be an entirely different kind of disaster. Here is the single most important thing to understand about that difference. Our modern infrastructure is built on long conductive networks, power transmission lines, pipelines, undersea communication cables that act like enormous antennas for geomagnetically induced currents. A Carrington-scale event today wouldn't just produce pretty auroras. It could trip transformers, disrupt GPS-based systems that agriculture, aviation, and shipping depend on, degrade high-frequency radio communication, and in worst-case regional scenarios, damage grid infrastructure badly enough to cause extended blackouts. Studies commissioned by agencies including NOAA and the National Academy of Sciences have modeled these cascading failure scenarios for over a decade, and the consistent conclusion is that the financial and logistical cost would be measured in the hundreds of billions of dollars, concentrated in the first weeks after impact. Connect that back to the filament we opened with. We are not saying this event is a Carrington-scale threat. Most coronal mass ejections are not. But the physical process, magnetic destabilization, plasma ejection, potential Earth-directed trajectory, is the exact same chain of events, just at a different point on the severity scale. That's why space weather agencies track filament eruptions this closely. It's not about this one structure in isolation. It's about what it represents in the current phase of solar activity. Now let's talk about the conspiracy angle directly, because it always surfaces after events like this. Some corners of the internet will tell you that solar activity like this is being suppressed from public knowledge, or that agencies withhold data on major solar events to prevent panic. That's false, and it's worth debunking clearly. Solar and space weather data is some of the most openly published scientific information available. NOAA's Space Weather Prediction Center posts real-time solar imagery, flare classifications, and geomagnetic storm forecasts publicly, updated continuously. NASA's Solar Dynamics Observatory streams full-disk imagery of the Sun to the public archive within hours. The information isn't hidden. It's often just not translated into language most people encounter day to day. That's part of why we're doing this. So here's what actually matters going forward. What should you be watching, and how do you interpret it without falling into either extreme, dismissiveness, or panic? Number 1. Watch the NOAA Geomagnetic Storm Scale. It runs from G1, minor, to G5, extreme. Most events that make headlines top out around G1 or G2. Those produce beautiful auroras at higher latitudes and negligible practical impact. G3 and above start to matter for satellite operations and high-latitude power grids. G5 is Carrington territory. Number 2. Watch for an actual coronal mass ejection detection, not just a filament eruption. A filament detaching doesn't guarantee a coronal mass ejection follows, and even when one does, it doesn't guarantee an Earth-directed trajectory. Coronagraph imagery from spacecraft like SOHO tracks this in near real time. Number 3. Watch the estimated arrival window. If a coronal mass ejection is confirmed Earth-directed, transit time typically runs between 1 and 3 days, depending on speed. That's your actual warning window, and it's short. Which is exactly why continuous monitoring matters more than reacting to headlines after the fact. Watch the classification, watch the trajectory. Those two data points, more than the raw size of any single filament, will tell you what's actually coming. Zoom out, and the bigger picture becomes clear. We are currently past the peak of solar cycle 25, but elevated activity persists for months to years after maximum, meaning filament eruptions and coronal mass ejection risk remain higher than baseline for the foreseeable future. That's not a reason for alarm. It's a reason for informed attention. The systems we depend on, power grids, satellite navigation, communication networks, were largely designed before space weather was well understood as an operational risk. Utilities and space agencies are working to harden that infrastructure. But the timeline for full resilience is measured in decades, not months. That is the real story hiding behind a striking image of plasma the length of 10 Earths. Not an isolated curiosity. A visible signal from a system that occasionally, and without much warning, reaches out and touches the infrastructure of modern life. Pay attention to the classification scale. Pay attention to confirmed trajectory data. And understand the difference between routine solar activity and the rare alignment that turns a distant eruption into a terrestrial event. If this kind of breakdown helps you actually understand the forces shaping our planet instead of just reacting to a scary headline, subscribe, because we track these systems continuously and we'll be back the moment the data shifts. Like this video if you want more of this kind of grounded, no-hype breakdown, and share it with someone who needs to understand the difference between a striking image and a genuine threat. Watch the scale, watch the trajectory. We'll be watching too.